record here. Okay, so yesterday we talked about sample means, and I'm gonna flip back real quick. I'll flip back to this page, don't worry. I'm gonna flip back real quick. We found that the center of the dot plot of sample means should be at the true mean. And we found that if the 10% condition is satisfied, that the standard deviation of that dot plot should be reduced by a factor of the square root of the sample size. So the bigger the sample size, the better, which is going to be true through all of stats. Okay. Do you guys remember my pathetic little picture I tried to make for you? I tried really hard over here. I tried to make you little normal curves and stuff. Okay, so today I'm going to do that again, but more official. So if you guys could just flip in your notebook back to this. So this is 7.3a. If you weren't here yesterday, just look up at the screen for the moment. I want to revisit this. It says the length of human pregnancies follows a distribution that is approximately normal with mean 266 days and standard deviation 16 days. Okay, are you guys with me? Okay, so what I did before you got here was I made this. Okay. I know this looks small. I need you guys to try to keep along with me. Try to stay engaged as best you can. It's just a demo for me. So, okay, what I did was I went into this software and I said, I want you to give me 5,000 different data points in a normal shape. You can't see it down here, but I said the mean is 266 and the standard deviation is 216. I wanted it to match that pregnancy word problem. And it gave me 500, a dot plot, basically of 5,000 entries, where the mean was 266 and the standard deviation is 16. Can you guys just imagine a normal curve shape over that? It looks pretty normal, right? Okay, and in the problem yesterday, I said that it was normal, true? Yeah. Okay, and that's the picture that I tried to make for you yesterday, but it was dumb. It was on a post-it note. It's terrible. Okay. Now, if you scroll down further into the problem on your notebook, it says we're going to take a simple random sample of 6 pregnant women. What's the mean of the sampling distribution? So this is my best shot, really, of getting you guys to understand what a sampling distribution is, other than the M&Ms thing. This and the M&Ms thing are my best shot. So what I did was up here in the top left, it says sample size, and I put 6, and then number of samples to draw, and it says max 10,000. So I'm just having it draw one sample. Okay, so I'm gonna go explain. Okay, so it drew a random sample of 6 of those dots up in that big normal curve. And you can tell one of them is here, one here, one here, one here, one here, and one is here. That's just random 6 different pregnant women and how long their pregnancies were. And then it calculated the average of those 6 and dropped it here. Okay, let me say that again. You have 5,000 data points up there. I tried to make it as close to normal as possible, so I picked 5,000 as the max it would go. It took a sample of 6 women, so 6 dots out of there. One was here, 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 here. Those are my 6 pregnancy links. And then those are averaged, and that one average is plotted on the bottom. Okay, that is called the population distribution on the top. This is called the sample distribution in the middle, because it's your most current sample. And then this one down here is not your sampling distribution, it's just one dot. If you had all possible samples, it would be a sampling distribution. So we call it an approximate sampling distribution. Okay, now what I'm going to do is I'm going to draw again. And I want you to see what happens. Okay. So it gave me a new sample. So it looks to me on this histogram that there are two of these, one of these, and one of these, right? And then it calculated an average, and it dropped that average down here also. So there must be two like right next to each other. There's two little tiny bars right there. And this is saying that there's two trials here, and there's my mean is at 261. You see it's not exactly 266, but that's pretty good. And my standard deviation is tiny for the moment. Okay, now what I'm gonna do you guys understand what's happening? So it's gonna take out a sample and it's gonna put the average. Take out a sample, add the average, just keep adding the averages down here. So I'm gonna do 10 more. Faster this time, without me having to walk back and forth. Okay, so I'm gonna hit 10 more. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Now, this has 12 averages plotted down. Does that make sense? Because I did one, and then I did another one, and then I did 10 more. So this is 12 averages. Do you see how less spread out this is than the original population? Okay, tell me what the standard deviation was that we calculated yesterday in the note. I think it was like 6.5.
6.53.
6.53, okay. And calculated by the 12 samples is 8.62. What do you think is gonna happen as I do more samples?
Just keep going down.
Yeah, it's gonna approach 6.53. And then what do you notice about the shape?
It's becoming more normal.
It's becoming more normal. Okay, so there's two things I want you to pick up from this. First, if the original population is normal, then the averages are going to be normal. I don't think that that's too far of a stretch for your brain. Original population is normal. When I average them, they're probably going to be normal. The second thing is the averages are less variable because you're dividing by the square root of n. You're making it smaller, a lot smaller. You see how spread out the top one is compared to the bottom. Okay, this is not fascinating. I'm not done yet. I don't really find this part fascinating. Do you? No. Well, probably not. Okay, but I do have something that is more fascinating. I promise. Also, just because we can, let's just draw 1,000 at once. So how do you feel about that being normalish? It's pretty good, right? Down here. And this graph thing is super cool. Look, I can put the normal curve over top of it. Okay. Now I'm going to completely reset this whole thing. And I'm going to do something more interesting. I'm going to take this. Okay. So, hold on. I have to hit refresh. It's a little touchy. Okay. I picked something that is super skewed. You see how skewed this is?
Yeah.
It's got bunches of stuff all the way over here, and then the tail goes out all the way to there. You guys see the skew? Okay. All right, now what I'm gonna do is I'm going to go with a sample size of 6 again. Just draw one. Okay. So. My population is super skewed. Does it make sense to you guys that most of the data points were from this range? And that the average would fall somewhere about here of those six? You guys get what I'm saying? So the bulk of the data is over here. So my six that I choose out of there is probably gonna come out of where the bulk of the data is. And we average it and it kind of comes to the middle of the, okay? Okay. All right, now, let's see what happens. This part's more fascinating, if you're me. Okay, I'll stop it there because this will tell my story pretty well. Can you guys tell that the sampling distribution is going to be quite a lot more, quite a lot less spread out? It's tighter together because there's averages. So look at the top, look at the bottom is tighter together, right? Less variable. Okay, but can you tell that it's still kind of skewed? Okay, now, this is fun. Okay, can you guys tell that it's still kind of skewed?
Yeah.
The bottom one, okay. Now, let me up the sample size, just the sample size. Oh my gosh, the excitement. Okay. I did a lot on the one. What's crazy is that the skew actually disappears and it gets normal. Did you know? Did you call it? Call it is gonna be normal? Okay, and you're like, of course it is, because we need to be able to use normal CDF. So all of the stats people created all these rules so that we could still use normal CDF. But you're kind of right. Yeah. But I think this is super cool because it starts off really wonky. And just from the sheer fact that these are averages, the tail just goes away and it becomes normal. Okay, so what is the biggest effect here? What did I have to change to make it normal? Sample size. And so sample size, it does two things for us. It makes it less variable, so it tightens up the data here, and it makes it normal. Okay, so now go to today's. So let's stop there, make sure that, write it down and then make sure you understand what it's saying. You draw many, many samples of the same size. So like needing the draw button. And calculate the sample mean for each. So you calculate the average, plot it, calculate the average, plot it. Does that make sense?
Yeah.
Okay, then. This thing is all about the sample size. Sample size governs everything. So what this means is when you're doing a study, research study or survey or something, you can't be lazy and just ask a few. You got to ask a lot. Okay. So there's two different things that we say for shape. The first one is okay, this one is not exciting. This is the one that I did first, that I said was very uneventful. The original population was normal, so the sampling distribution ended up being normal. Okay, not fascinating. You kind of expect that to happen. Shape of the population is not normal, like that skewed one that I put up there. Okay, so this is one of those things. Everyone in the whole world that does stats pretty much agrees on 30. 30 is the sample size necessary to be normal if the shape is terrible. That's why I put 30 in the one that I did that was super skewed. So you're just going to have to check your problems to see if the sample size is bigger than or equal to 30. And if it is, then you're set to use normal CDF. Okay, so how do we write that? We'd write something like this: shape
N equals, what was this? Let's just pick a number. 50. So let's pretend that you're doing a problem. Sample size is 50. You would say 50 is greater than or equal to 30. So CLT applies. The people that grade the AP Stats exam know what CLT means. You can abbreviate central limit theorem to be CLT. You can abbreviate it in your homework, on my test, on the AP test also. So you do not need to write out central limit theorem every single time. It's just CLT is good enough. Okay. I see, like, with these problems, the goal of them really is to do normal CDF when you have these probability questions. It's really hard to calculate probability with a skewed distribution. They're all different. So what we do is we use a sampling distribution that's normal. Okay, but the question is, what things do I need to be able to do normal CDF? What's the stuff that's required? There's a few things. What do I need? I'm going to put a little list over here. Yeah, I need standard deviation. I need mean, high and low. I need one more thing. Okay, let me point an arrow to what I'm referring to. Yeah, I need it to be normal. I can't use normal CDF on a right skewed distribution. Okay, so we need all of this stuff to be able to do normal CDF. I think we start with the shape being normal. So shape. What is n in this problem? 40. Okay, so you say n equals 40. 40 is greater than or equal to 30. So CLT applies. Okay, now pause real quick. This is very easy to do, to check off. It's like, easily check off. Oh, now I get to use normal distribution. Now I can use normal CDF. But when you're doing this, I don't want you to forget that up on the top was a really skewed graph to the right. And then there was a sample, and then they averaged it, and those samples dropped down and made a nice little normal curve on the bottom of the screen. Do you remember? We had a skew, we had a sample, and then all those averages at the bottom were normal. Like, it's okay You're not just like, you're not just being like, oh, assume it's normal. No, it really is because because we're not talking about the population graph, we're talking about the dot plot at the bottom, which is normal. Okay, anyway. Okay, center. The mean is the mean. Spread. Is the standard deviation of that dot plot at the bottom the same as the graph at the top? No. Yep, so 20 divided by square root of 40, which is something, 3.162. Okay, now do we have everything we need? Okay, so we're going to start with our low and high next. Exceeds 35 minutes each. Yeah, so it's going to be x is greater than 35. Exceeds means greater. Oh, I forgot to write normal CDF. Gosh. Just went straight into the parentheses. Okay, now I want to show you something about normal CDF I might not have shown you before. Wait, there's more, Mrs. Talbot? Yes. Is anyone in here just so unbelievably lazy? So what I did when I do these, because I'm just so lazy, is I actually type the math. Yeah, type the math into the stick. I know, but look, it's fine. 0.056 times. Okay, there's one more part and then we're done. Do you guys have any questions about this? Okay. So you believe me that it's normal even though it says right skewed? Because it's not talking about the same graph, right? Okay, that's the same. Okay, last thing. This set of questions comes from my husband's work because they never give them enough time to do the services on the card. They're always like screaming at them and yelling at them to go faster. So I must have made these word problems up on a day that he was unhappy with his work, which is often. Okay, and this is going to be a little blast from the past just because I think it's good for your brain. Okay. How much average time per customer should they budget if they want to be 99% sure that they've given the technician enough time? Okay, so we're gonna say probability that X is less than or equal to something. I want to put a question mark there. Some amount of time is 99%. We haven't done this in a while. Yeah, this is inverse norm. Yeah, okay. So inverse norm works on less than or equal to, so that's what I did here. So let's talk about inverse norm and what it needs. Unfortunately, I did this problem before you came and it's all typed in here. Hold on. Okay, sorry, there we go. Had to clear it out. Okay, so inverse norm needs an area, a mean, a standard deviation, and a tail. Our tail is going to be left because our thingy's going less than or equal to. So our area, 0.99. Mean was what? 30? And standard deviation was 37.4. So they need 37.4 minutes. Not the 30 that they're given. Anyway, that might be just the wife of a auto technician speaking there. Pastor here gonna be sad all the way up. Okay, so that's it. You guys are like super important to me about the graph. Doesn't matter what it is on the top, as long as n is greater than or equal to 30, it'll come out normal on the bottom. Okay?